Welcome back! Let's see how to create the systolic array for our Smith-Waterman. As we discussed in the previous lessons, we will avoid calculating the maximum index, hence, let's delete it from the code. Notice that we do need to remove also the related interfaces. Now, in order to go fast on the FPGA, we want the data to be as local as possible. To do so, we need to copy our input variables into local buffers. So, let's define two variables for our input strings. As I am lazy, and I'd like to avoid changing all variables' names, I am changing only the variable passed as parameters in our function, adding the suffix _g. Once defined the local variables for the two input strings, we can copy the values from the DDR to our kernel using the memcopy function. Here, we are defining also two local buffers for the similarity and direction matrices. However, we just need to copy the final results back to the DDR. Hence, we can place the final memcopies at the end of our kernel. Let's try to synthesize the kernel now, in order to have some feedback on the performance of the architecture that we are implementing. Oops, wait, we have an error. I forgot to remove the variables regarding the max index and to include the library to use the memcopy function, that is string.h. I even forgot to change name of the variables when I defined the interface with the memory, so let's change them too and synthesize again. Great! It's synthesized. Let's see the performance estimates for our loops. First of all, we can observe as actually the memcopies are implemented as pipelined loops, and we are able to achieve the II of 1 for both the reads from the DDR. However, the II of the central loop is equal to 2, and then the one of the final store is equal to 15. This means that both these loops are not able to produce an element each clock cycle. Let's have a look at the log in the console to better understand why our kernel is not able to get the II of 1 on all the loop cycles. We can observe from the loop that we have a dependency among different operations on our central loop, while on the final cycle, there is a dependency with the memory. Basically, when we try to write multiple times to the memory, we have to wait as the memory is not able to keep up with the amount of data we are providing at each clock cycle. We should be able to solve this first dependency specifying our systolic array architecture, while, for what concerns the second one, we will solve it later by trying to compress our output data. Another important information we can find in our log regards memory burst inference. Usually, when we want to read or write to the DDR memory, for each element to transfer, we need to specify the address of the location in memory where to fetch or store the data. However, thanks to the memory burst, we are able to provide the address only once and transfer big consecutive chunks of data to and from the DDR. Let's now move on in implementing our systolic array architecture. One of the first things we can optimize regards the usage of the similarity matrix. Actually, we do not need to store entirely the similarity matrix, as at the end, we are just interested in knowing the directions to follow. The only thing we need are the dependency values for our processing elements. We can in fact delete the similarity port and removing its interfaces, and declare 3 buffers for the dependency values. These buffers are the one that contains the north, west, and northwest dependency values, and need to be sized as the size of the query plus 1 elements. We will see later on why. For what concerns the direction matrix, each processing element produces 1 result to store in the direction matrix. In the systolic array we want to implement, we want to instantiate n processing elements. Hence, we need a buffer with size n, so that each clock cycle we can store the result of each processing element and then store it into the DDR. Now, the first loop I am implementing here, it's necessary to initialize all the elements of our dependency buffers. In order to perform it as fast as possible, I am also asking the synthesizer to pipeline the loop. Now, we need an external for that iterates for each antidiagonal we want to compute, namely n plus m minus 1 times. Inside this loop, we have to write the code to perform the computation of an entire anti-diagonal. Let's define a function to perform this computation. Inside this function, we need to define a for loop that iterates for all the elements of an anti-diagonal. We will completely unroll this loop so that we will be able to compute all the elements of an anti-diagonal in parallel. Inside the loop, in fact, we are defining the operations that will be performed by each processing element. The loop will have to start from the end of the anti-diagonal to 0. I have implemented the loop in this way because otherwise the kernel will produce wrong results when executed in software emulation, due to how the dependency buffers have been implemented. Let's now move over to specify the logic for the processing element. We need to basically write the same operations as in the previous version of our code, but let's specify them so that the synthesizer can understand better what kind of architecture we are expecting. So let's read a character from our query and one from our database. For each call of the calculate diagonal function, the index of the database character depends on the anti-diagonal we are computing now, as you can see from the first line of the code of this function. Now, let's use a match variable to store the results of the comparison between the query and the database character, and let's calculate at this point all the three values val1, val2, and val3, as in the previous code. Now, our code needs to identify what is the maximum value among these three. To ease the synthesizer task, I will specify every possible case in our if condition. For each branch here, I will specify first the dependency values that needs to be updated, and then store the direction in the correct index of the direction diagonal buffer. The code then is basically the same for each branch. However, we are storing every time a different value. Notice here that each processing element updates the northwest and west dependency value of the successive processing element and the north value of itself, to be used in the next clock cycle. Finally, we need to update the database local index to reflect the correct database character to fetch at next iteration. Awesome! We have defined the basic behavior of n processing elements. Now, when executed in parallel, this processing element will produce in one clock cycle, or at least this is our objective, n elements of the direction matrix that needs to be stored to the DDR memory. We need now, in fact, to specify how to store the direction diagonal. Let's define again a function called storeDiagonal. This function basically calls a memcopy function to the DDR, hence to the direction matrix _g variable, but as we are computing a diagonal every time this function is called, we need to provide an offset to this variable, that in our particular case is the directions index variable. Finally, we just have to update the direction index variable to reflect the next index we will have to store, and we can clean the old code from our kernel. Great! We have defined the basic systolic architecture for our Smith-Waterman algorithm. Now, we are ready to synthesize it in the next lessons.